and also the class of algorithms to which they belong. There are three key things about support vector machines. One is, it turns out in practice, they're one of the most widely used, most successful approaches to training classifiers. Another is that they're based on an idea we haven't talked about so far, which is maximizing the margin as an objective function for choosing our weight vector. And third, they are based also on the idea of kernel functions, which I promised last time we would be talking about. So we're going to talk about all these things today. So let me begin with reminding us that what we looked at last time, just a little bit of notation to get us all on the same page. So we've been talking for a long time about learning linear functions as a weighted sum. If we have a vector input x containing features x1 through xn, then our typical linear function would just take a weighted linear combination of those features. And we can express it that way, or to use shorthand notation, we can really use the fact that these are vectors and use vector notation. So in general, I'm going to use bold font to represent vectors. So I can write the same expression as the dot product, or equivalently called the inner product of two vectors, which is just defined by that linear sum. Another notational variant of that we'll see is to think of a bold font character represents a vector which is a column vector, like this one over here, and we'll take its transpose, putting a superscript t, to mean that we're rotating the vector into a row vector. And then we can think of the dot product, or the inner product of two, of a row vector with a column vector as just literally this sum. So it's just notation. And last time we talked about how we could use that notation to re-express our objective function. Of course, our learning problem is to learn those components of the w vector, the weights, that we're going to multiply against the components of the x vector to predict our scalar value y. And we noticed last time that if we like, we can express that as saying, well, we want our w vector to be the w that minimizes this expression. And the first term in that expression is just the difference between y super L, that's the observed value for the Lth training example of y, and the difference between that and our prediction, which is just the dot product of x super L transposed, of course, with w. So that's our sum of squared errors term. And also, if we want to regularize, for example, to minimize the sum of the squared values in the w vector, we add that in as well. And then we pointed out we could represent this, in fact, in even more compact notation. If we say, well, let's just take all of those different training examples, and let's make y be the vector of all of the observed y values for all the training examples. Similarly, let's make the matrix X be a matrix where each row, in fact, the ith row, is just the ith training example. And of course, we have our vector w. And now we can represent this whole first expression by just saying we want to minimize the square of the difference between this vector of y training values and w times the x matrix of training examples. Okay, so this is all notation, but I wanted to start by quickly saying it again because we will be using it today. Okay, so here it is in prettier font than my handwriting, just so that everybody could read it. And so I want to start by, again, just kind of swap in a little bit of notation and also intuition. Many of you have had courses in linear algebra. You're familiar with this. But it's still good to just very briefly notice that there's a geometric interpretation we can take of this notion of a dot product or inner product. So suppose, for example, that I'm trying to learn this function, and I've decided here is my learned weight vector. And I have some point 3, 1. Then if I call this the first component of the x vector and the second component, I could plot that point, of course. By, let's see, x would be 3, 1, so 1, 2, 3, 1, x would be here. And w, if I wanted to plot w, it would be 1, 2, so it's 1, 2, w would be here. And in fact, I can think of those as vectors, as directions in this space. So I can think of them as vectors coming out of the origin to their points. So I could think of w either as this point or equivalently as the vector from the origin to that point. It's really the same thing. But then what's interesting is when I think about the dot product of two vectors, of course we have our definition of it. It's just what we said it was. But we can also think of it in terms of the length of these vectors and the angle between them. So for example, if I'll call this angle between w and x theta, then it's also the case that their dot product, defined this way, is equal to, this is the length of x and the length of w times the cosine of the angle between them. And you can prove this to yourself rather easily, but it's a simple fact. And I find this very useful when I'm thinking about vector algebra and linear algebra to keep this in mind. So, for example, it helps me think, well, let's see, if I have this vector and let's say this vector, then one way I can think about its dot product is I could think, well, here's theta. I could think, well, what if I just project the endpoint of that vector onto x perpendicularly? Then what this product, what this distance is going to be, of course, is just w times cosine theta. That's high school trigonometry. And then if I take that projection and multiply it by the length of x, actually I should have put my bars around there, meaning the length of the vector w times cosine theta. So I can think of the dot product as that projection just times the length of x, which is exactly what we're talking about here. Okay, so that lets me easily see little facts like if I don't change w and I don't change x in terms of their length, but I allow them to rotate around their origin, then you can quickly see the answer to questions like, how would I have to rotate them to make the dot product 0? Just make them perpendicular, right? Rotate w until it's perpendicular to x. Now, obviously, x cosine theta is going to be, or w cosine theta is going to be 0, and it'll be 0. How would I rotate them to give them the maximum dot product without changing their length? Just make them collinear, in which case cosine theta is 1, and it's just the product of the length of the two vectors. And everything in between is something in between. So that, for example, you now know the dot product will never be greater than the length of x times the length of w, and it'll never be less than 0 is the wrong answer. It'll never be less than the negative product of their lengths, right? They can point in opposite directions, in which case, look at that. Okay. All right, good. So we're swapped in on vectors. Those ways of thinking of things are going to help us. All right, so talking about linear regression again. So here's our equation again. We want to learn some linear function of x, just the dot product or inner product of the input x with our weight vector w. And we want to minimize the sum of squared errors plus this regularization term. Then the way to solve this is the same way we talked about before. We could take the gradient of that objective function, the thing we're trying to minimize with respect to w, take the gradient of that with respect to w, sorry, take the derivative of that with respect to w. Well, I guess it is a gradient. Set it to 0. And if we tediously worked it out, we would find that here's the expression that gives us the optimal vector of weights w. And just looking at that for a moment, what we see is in there is, so w is going to depend on the vector of y's. In fact, if we double all the values of y's and leave all the x's alone, then we'll just double the weights w. Which makes total sense, right? We're talking about linear regression. So if you scale up by a factor of n the values y, then you're going to scale up by a factor of n values w. And also, let's see, what is this x transpose x thing? Of course, the transpose is just the rotated matrix. So what that x transpose x is doing, x, remember, is the matrix, each of whose rows is a training example. And so x transpose is the same matrix, but now where each of its columns is a training example. And so we're looking at some kind of weird combination of dot products of features across examples. So that's a little harder to, I don't know a simple way to. Right. So that's like correlation. And then we're taking the inverse of that. So anyway, the point is now if I have a new example that I want to classify, all I have to do is multiply it by my weight vector. Or equivalently, if I cared, I could just multiply it by that less efficient combination of things. Okay, and this is called the primal form of linear regression in the sense that, well, it's the primary way we think of the problem, I guess is the way to say it. And like many of the learning problems we've talked about, we're framing this as an optimization problem. There's our objective function, the argument over w. Here's the solution to it. And under the probabilistic model we talked about earlier in the semester for linear regression, this is actually the map solution for the weights. The maximum a posteriori probability weight vector corresponding to minimizing the sum of squared errors plus this regularization term which comes from our priors. Okay. Now, there's an interesting observation we can make, which is that this weight vector actually lies in a space that is spanned by the training example vectors. What does it mean to be in a space? What does it mean for a set of vectors to span a space? Same as we talked about when we discussed PCA and we talked about different coordinate frames. And we said, well, a coordinate for what it means for a particular coordinate frame to span a space is that The space is a set of vectors, the space that's spanned by this is any vector that can be represented as a weighted sum of the unit vectors along the different coordinate axes. So, so this vector, and this vector span the three-dimensional space in which this point exists, for example, because this vector could be represented as a weighted linear sum of the three that I just mentioned. And in the same sense, what's interesting here is that the weight vector that we get in linear regression lives in a space that is spanned by the training examples, which is actually kind of interesting. Now, why would that be? Well, let's think about some training examples. So here's suppose I have a two-dimensional space. I'm going to call these, maybe I should call them U1 and U2 so I don't get messed up when I'm going to use subscripts for x's. But now here's a training example, x1, and maybe it has a y value 5. So there's a training example. That corresponds to a vector. Here's another training example, x2. Maybe it has training y value -9. It's another vector. Well, one thing that's obvious is just like U1 and U2 span that plane, that is, I could represent any vector in the plane as some combination of some weighted sum of a U1 plus a weighted sum of U2. I can represent any vector that way, right? Similarly, instead of U1 and U2, I could use x1 and x2. They also span that same plane.
But this doesn't really say anything. What I guess is meant by this is that something lies in the subspace spanned by the training vectors.
Right, right. So we're getting there. Just hang on. So x1 and x2 obviously span the same space as u1 and u2, right? And so as long as w lies in that space, then x1 and x2, then it lies in the space spanned by x1 and x2, the training examples. Okay, so now what would it take for w to not live in that space? Right, w is the same dimension as the x's, right? We're taking dot products of w with the x1s. So the only way w could not live in the space spanned by x, by the training examples, would be if somehow we had 3 features instead of 2. We had u1, u2, and u3, but the data points happen to just live in a plane within that 3-dimensional space. Right? In that case, we could consider the possibility that w is not in the same plane that is the subspace occupied by the training points. Right? So for example, let's do it that way. This table is u1, u2, and my perpendicular thing coming up here is u3. So I could say, well, I have training examples. They all have 3 features. But just the way it turns out, they all happen to have, let's say, the same value for this feature. So they just live in some implicit 2-dimensional space. In general, in fact, it wouldn't even have to be parallel to one of these axes. It could be a plane like this. But the thing is, the only way w could not live in the same space is if the training examples somehow occupied a lower dimensional space, even though I was describing them in terms of 3 components. They're only really living in a plane anyway. And then I could worry about the case, oh, well, then maybe w isn't living in the space spanned by those. But now think about it. The way I set up my objective function, I said, what am I trying to minimize? The sum of squared errors in those dot products between w and x predicting the function, plus a negative term penalizing for the length of the vector. So think about it this way. Let's make this table surface the two-dimensional space in which those points live. And suppose I consider this w does as good a job as can be done in minimizing the sum of squared errors for the y values and the x's in that plane. In that case, there's going to be another w that I could have chosen instead that's shorter. It's just the projection of this w into the plane that those examples actually do live in. Its dot product is going to be, with each training example, will be identical to the dot product of this longer w that doesn't live in the plane. And because of my regularization term, which is penalizing for the length of w, my objective function is going to prefer the one that actually lives in the plane. Because even though both of these vectors have the same sum of squared errors, the shorter one that lives in the plane will have a smaller Okay, so that's an informal kind of explanation that gives you some insight into why w lives in the same space spanned by the training examples. We can be more formal, although I don't want to go into too much. Did I really? Oh, no. I see. We can be more formal and prove it, but I don't want to do that here in class. But it is a fact that the weight vector w does live in the space that's spanned by the training examples. And therefore, if we want to, we can repose our primal form optimization problem in a different way. We can use the fact that w lives in the space spanned by the training examples. What does that mean? Well, that just means, of course, that w can be represented as a weighted linear combination of those training examples. So let's write it down that way. Let's say w actually is the sum over all the training examples of some scalar constant times the elf training example, and we're summing this over all of the training examples. Okay, so this is just saying that w can be a linear combination of those training examples, that it lives in that space. But if we'd say that way, then we can re-express the function that we're trying to learn this way. Right? Instead of saying we're going to take the dot product of x with w, we'll take the dot product of x with this thing. And because this is just a constant, we can pull that outside the dot product. And so it's the same as the sum of the dot product of x with w is just the same as the sum over the training examples of the dot product of x with the elf training example, weighted by alpha, which is its coefficient along that direction. Okay. So again, all we're saying is if here's training example 1, here's training example 2, all we're saying is there's some alpha 1 that we can multiply x1 by, plus some alpha 2 that we can multiply x2 by, and we can get any weight vector that's in this plane by picking alpha 1 and alpha 2 appropriately. And if those are my only two training examples, since w lives in the same space spanned by those, I'll always be able to do that. Okay, so this is actually pretty interesting. It's a little weird to think about, but what this is saying is if we wanted to, we could classify new examples by a new example x, we're going to classify it by storing up our training examples, take the new vector in that we're trying to classify. What we'll do is we'll run through the training examples one by one. We'll take the dot product of the new x with the ELF training example, multiply the result by alpha L, and then add that and add that and add that. And furthermore, if we work out the algebra, we can get a closed form solution for what those alphas are, which looks like this. And notice here is our old form for W. This one also has an interesting change. Instead of x transpose x, this is in the form of x transpose, which is actually quite interesting because what is that? Remember, X is the matrix where each row is a training example. And so X transpose is the same matrix, but where now the training examples are the columns. And so what is the ijth element of X times X transpose? It's just this column times this row. So every element in X transpose is itself a dot product of two training examples. So this is like dot product city. If we know the values of alpha that we're trying to learn, we can classify a new example X by taking its dot product with every training example, summing them up weighted by alphas. How do we solve for alphas? Well, we solve this expression, but the only really complicated part here is this X transpose. How do we calculate that? By taking dot products of different training examples. So this is like really interesting because what it says is if we could do dot products very efficiently, we could solve this learning problem, and then we could apply our learned stuff very efficiently. And that's actually why we care about dual form, it turns out. Because the idea of kernel functions is that they're going to give us a very nice, pleasant, ridiculously fast way of doing dot products in high-dimensional spaces. And then furthermore, support vector machines are going to assure that when we do this, most of the alphas are 0, so we don't even have to sum over all the training examples. It'll be more like the same number of examples that are the dimension of the space that's spanned. So there's a lot of good stuff coming out of this dual form in a second. Okay, so before we leave that, I said that we could actually derive the expression, and I wanted to include these slides. By the way, a number of the slides that I'm using are from John Shaw Taylor, who wrote a textbook on kernel methods and support vector machines, which is very good. Also, some are from Eric Singh and from R.T. Singh, who have taught this course in the past. And so here is the derivation for how we solve for alpha. And I'll just go through this very quickly, but you could study this more at length. But the key thing, again, is that the dual solution expresses the weight vector W as a linear combination of the training examples, as we said. And this is the expression that we get when we solve for W in the primal form. This is an expression that relates W to X's and Y's. It's just a rewrite of the solution that we put for our primal form optimization. But if we manipulate terms in here, we can notice that W can also be expressed, the optimal value for W, the W that minimizes our objective function, satisfies that top expression. And so the optimal W also is equal to this. And what's interesting is this term, you might say, well, there's a W left here. But if you think about this term is just the errors that the optimal W makes. It's y minus W times x. This is just the vector of errors that it makes. And when we solve for the optimal W, the residual error, we're solving for a linear function and maybe the function isn't exactly linear, so there's some unavoidable residual error. And that's what that expression is capturing. So we can think of that really as a constant. It's just a property of the data set. It's not changed by which W we choose. It's just the best residual error one can get given this data set. And so if we think about it that way, we realize essentially we can write that expression as just x. Oh, I should warn you, John uses prime instead of t for transpose. So that's just x transpose times 1 over gamma times that is just x transpose times, well, let's just make this whole thing a constant and call it alpha. And that's our vector of alphas for the training examples. So this is actually the derivation of the proof that indeed W is a linear combination of the training examples. And he's using subscript instead of my standard superscript for talking about the ith training example. So this is actually a more formal derivation of the fact that W does live in the space spanned by the training examples by showing that we can express W this way. And as a side effect, we get the solution by then substituting this thing back in. That gives us the solution we were talking about that we had on the previous slide. And again, I include this more for you to go through in more detail later as you like. Okay, so the bottom line is this. We can solve our linear regression problem either in the as the primal formulation, picking the W vector that optimizes our classification performance according to that objective function, or equivalently, picking the alphas that minimized exactly the same objective function. And so if we want to do that second one, use the dual formulation in terms of alphas, then here's what we do. Step one, we collect our training examples, all the x's and y's. We pack them up into the X matrix where each row corresponds to one of our training examples. The y vector is just the vector of the different y values. And then we compute alpha, which is going to be our vector of weights for each training example. And here we've written this as k, where k is, again, x times x transpose. And as we said before, each element of that x times x transpose matrix, when we multiply them together, the ijth element is just the dot product of two of our training examples. That's what we said. So that's step one. We solve for alpha in terms of that. And then we classify our new point accordingly. But here's the key thing, and just as I suggested before, all we have to do is dot products and nothing else. And so that opens the door to the key thing about kernel functions. What is a kernel function? A kernel function is a function that allows us to compute the dot product in some high dimensional space of points living in some high dimensional space by calculating some other function in a low dimensional space. That's what we use kernels for. So let me skip ahead one slide and draw a picture. So here's the way to think about kernels. Suppose I have some original two-dimensional space. I'll call my dimensions, here I have unit length, U1 and U2. But, and I have a couple points in this space. Let me call them x1 and x2. But now I have some other higher dimensional space that I would like to be working in. That looks kind of like this. This is an artist's conception of a three-dimensional space. Sorry, it's a non-artist conception. And now, in the spirit of the last couple lectures of projecting points into different spaces, suppose I have some function phi that, let's call this space 1, and this is space 2. Let's just call this Euclidean space of 2 dimensions and this Euclidean space of 3 dimensions. So I have some function that can map from R2 to R3. So for example, I'll say phi maps this point into this point in 3-dimensional space. I'll make that one big because it's close to you. And it also maps this point over here. Make that small because it's far from you. Okay, so I have some mapping that projects my points into some high-dimensional space. Then what the kernel function does is it lets me ask, let's see, I would want to, so I'm going to call this one just phi of x1. I won't give it a separate name, or sorry, phi of x2. And this one is phi of x1 here. So I might be interested in the dot product of these 2 points in the high dimensional space, phi of x1 and phi of x2. And what a kernel function does is it gives me some other operation. I'll call the kernel function k. K of x1 and x2, which is a function defined over the original space. In fact, k maps, in this case, R2 to just R. But the thing is that k equals the dot product in the higher dimensional space. So if we can, so this is the idea of a kernel function. It gives us a way, if we have points in some low dimensional space, but we'd like to find a linear function up in some higher dimensional space. Why? Perhaps because the function we're trying to learn is not linear in this lower dimensional space. And so we come up with some way of mapping these points into a higher dimensional space. But now, if we're going to use the dual form of things to solve our linear regression up in this higher dimensional space, we know that the only thing we have to do is dot products. And so kernel functions become incredibly valuable because they give us a way of effectively doing linear regression up in this high dimensional space without ever projecting any of the points into that high dimensional space. Because anytime we need one of these dot products, we just use k. Okay, so what's an example? Suppose, well, actually our example could be we're trying to do linear regression as we were talking about, and our function isn't very linear. Maybe it's a quadratic function instead of a linear function of u1 and u2. Maybe it's a quadratic function of u1 and u2. Well, what we can do is we can define, we'll see in a second, a phi that maps each of these points into a three-dimensional point where linear functions of these points do correspond precisely to quadratic functions of these points. And so basically, by using this kernel idea, what we can do quadratic regression instead of linear regression by introducing just this simple kernel function on the points that are still living in 2D space. It's equivalent to the much more computationally expensive thing of projecting all those points up here and then doing linear regression up here. Instead, we're just doing it down in the base space using this kernel function instead of simple dot products. Yes?
What do we gain over doing quadratic regression in that space?
Over doing quadratic regression in this space? What we gain, and I'll have an example of this in a second, but what we gain is computational complexity, because the kernel matrix, here's actually a very important thing to notice. What is the dimension of this thing? The dimension of this is number of training examples by number of training examples. And so in a two-dimensional space, we're not gaining much by going from, actually, let me go back one slide. Here's the place. Here's the place to put. So this thing is number of training examples by number of training examples. What's this? What's the dimension of that? It's not number of training examples by number of training examples. Right. This is the number of dimensions of the data by number of dimensions. And so if we're in a situation where, let's say, X is pretty high dimension already, but we only have a small number of training examples, then we're going to be better off doing this. And so let's take a look at an example like that. So let's play this out. Here is the projection that will take my points in 2D space into points in 3D space. And here is the corresponding kernel function that we can use in order to do things. So let's see what this means. So my points in 2D space, let's just call them x1 and x2 are the coordinates. So bold x is my vector. These are just the two components of an arbitrary vector in the two-dimensional space. I'm going to define the function phi such that it has 3 components instead of 2. The first of these components is just the square of x1. The second of these components is just the square of x2. And the third one is the product of x1 times x2 times the square root of 2. Okay, so now think of this. If I do linear regression on this, I'm going to be multiplying that by W1, W2, W3, right? I'm going to be learning a W1, W2, W3 vector, take linear combinations of those. That's precisely quadratic regression. So doing linear regression up in this expanded space gives me quadratic instead of linear regression effectively. And furthermore, here is the kernel function for that particular phi. Every projection phi that you define might or might not have a corresponding kernel function that allows you to, instead of projecting the points and then getting their dot products, if we have the kernel function, we use it and we apply it just to the original two-dimensional points. And in this case, we can do that because the kernel function that goes with that phi is just the dot product of xi and xj in the original space squared. So this is something you could work out at home, but it's actually not hard to prove to yourself that indeed, if you take x1, x2, and for another vector, let's call it z1, z2, and you get the dot product of those and square it, you'll get exactly the same number as if instead you project them with my phi up there and take that dot product in the three-dimensional space. You'll get the same number every time. Okay, why? Because this is the kernel function that pairs up with this particular phi. So if we're in a situation where we know the kernel function, then our quadratic regression problem turns into the following linear regression problem that we just talked about. So what we're going to do is, instead of saying f of x is alpha times the dot product of x with each training example multiplied by its alpha, now I've generalized just a little to say kappa. Now, if I want to work in the original space, then kappa is just literally the dot product of x times xl. If I want to work instead virtually in this three-dimensional quadratic space, then instead I say, well, kappa is the dot product of x times xl squared. So with that one little operation, redefining kappa not to be just the dot product of these, but the dot product squared, I can do all my operations. Here again, now the elements of the ijth element of my matrix K is no longer the dot product of I and j training examples. It's the kernel function of that. And again, if I want to operate in the original space, I just define the kernel function to be literally the dot product. So you see what's happening here. We're being able to do computations down in the original low-dimensional space that correspond to doing linear regression in exploded spaces. Yep?
So if you do linear regression in this exploded space, is it actually the same as doing it in the 2D space? Because there's a different form of, linear regression assumes a certain form of the errors on your variables. So is it actually the same?
I see what you're saying. I see what you're saying. We're actually solving for the W's in the exploded space. Right? Because if you think of the derivation we went through, even though it went through kind of quickly, it's literally the case that if we solve those formulas that involve the dot products, we will be able to calculate the W vector in the primal space that minimizes the exact objective function that we talked about. And if we went back through and re-derived it by everywhere we had x putting phi of x, then the derivation would look pretty much the same, except that everywhere we had the dot product of two training examples, we'll now have the dot product of phi of example 1 and phi of example 2. And so we're literally solving the same linear regression problem in the exploded space, but the computations themselves are operating in the smaller space.
But then the error is defined in terms of exploded space.
Right. So it's literally, it's equivalent to what if we really exploded all of our points into phi and then used exactly that objective function. It is really the sum of squared errors.
Yeah, but the error between phi y and phi x isn't really the same as the error between y and x. So you are using a different objective function than you usually.
Well, it's as though you, right, it's what you would get if you just ran standard linear regression after transforming the data using phi.
Yeah,
It really is. It is, because it's the sum of squared errors that you're minimizing.
yeah, but what I mean is that by using this kernel method, what you are the objective function you are actually optimizing is the error some square error between phi x and phi y, not x and y. It's a different function than the normal quadratic regression.
True. Right. It corresponds to doing linear regression in the exploded space, which is not the same.
Yeah, so it's not really correct.
Right. So, very close. But the basic thing you see is that it converts this into a quadratic regression problem inexpensively. Okay, so now let's see where this might make sense. So suppose that our regression problem has as input images. Say images with 1,000 pixels. So the original dimensional space we have is 1,000 dimensional. Every image lives in a 1,000 dimensional space where each pixel is one dimension. And suppose I want to do regression, but effectively quadratic regression. So I use that kernel that we just talked about, and I explode the images into a higher dimensional space. So now in this case, the quadratic thing I'm going to, when I explode it, my phi is going to end up having a dimension for every feature product, every pixel product, every product of pixels out of the 1,000 pixels, there's going to be a feature in my exploded space, in the quadratic space. And so instead of having 1,000 pixels in my base space, I now have 1,000 squared features in my quadratic space, which is 1,000,000. So now I'm operating in a 1,000,000 dimensional space instead of a 1,000 dimensional space. And now you see the beauty of the dual formulation combined with the kernel. Because now when I solve this as the dual formulation in the base space using, instead of dot products squared, I'm basically, first of all, if I have 1,000 training examples, I've got my X transpose times X matrix is 1,000 by 1,000, whereas my number of features by number of features matrix is 1024 by 1024, so I already won there. But then, furthermore, I get to do quadratic regression instead of just linear regression. So I'm both getting a larger, a more expressive hypothesis language and doing it more cheaply. So this is the kind of situation where it can really help. And furthermore, what if I didn't want to stop at quadratic? What if I wanted not just to consider features which were pairs of pixels multiplied together, but what if I wanted combinations of feature triples, pixel triples? Then I have 1,000 times 1,000 times 1,000 in my exploded space dimensions. I guess that's 1 billion. But again, if I have the right kernel, and I'll give it to you, it's the dot product cubed. I can operate in the original space, effectively doing linear regression in this billion-dimensional space. So it's a big win when you do, when you look at problems like that. So here's some kernels. We just saw one of them. So again, k is our kernel function. And what we just saw was the case where we take essentially the dot product, the kernel function for two vectors is the dot product squared. that gives us polynomials of degree 2, quadratic regression. If I want cubic, then I take the cube of the dot product instead. If I want polynomials not just of degree d, but of all degrees up to d, then I take the dot product plus 1 to the d exponentiated to d. If I want to use, here's another kernel, which essentially in the base space, what this kernel is doing is, it looks a lot like a Gaussian function, right? It's taking the distance between the two vectors as though giving us this kind of Gaussian-like distribution based on the distance between the two. And that corresponds to an infinite dimensional linear regression problem. So that really saves on computation. And then here's another sigmoid, like our former logistic function that we've talked about. So these are all examples of kernels where there exist corresponding fees, which, of course, we never actually, our algorithm never has to actually operate with those fees. The fees are just for our own benefit, for understanding what's going on as being equivalent to being linear regression in some exploded. Is kernel regression in the base space. Kernel regression, just the same linear regression, but instead of saying dot product, we say function k of those two things instead of dot product of those two things. Here are the k's, and there are some of the for which we know the corresponding fees. So it's a very generic, very general and powerful idea. And it makes you wonder right away, well, which functions can be kernels and which fees can have kernels? And the good news is many useful ones, and the bad news is not everything that you think of. The story gets complicated, and that's why there's a lot of work in this area. In fact, kernel methods became very popular around 2000 or so. And then there was a whole burst of papers that came out where somebody would say, hey, I found a kernel for this fee, and they'd publish a paper on it. Now all the easy ones have been found, and it gets harder. And then people moved on to, well, the original work was all about kernels in Euclidean space, like the example we talked about. But now people are looking at, well, what if my x's are not points in Euclidean space, but they're strings, like words or phrases? Or what if they're graphs, and so forth? So people are now making up kernel functions. You can imagine you have to kind of generalize your way of looking at what it means. But basically, kernel function means, according to some definition of an expanded space, there's an operation you can perform down in the base space that corresponds to inner products in the other space. So we're not going to, in this course, go into detail on this. If you're interested, get John Shaw Taylor's book. It's a very nice book about kernel methods, and it really goes into a lot of detail on this. Okay, but for us, here are the key points. For us, many learning tasks are framed as optimization problems, that's for sure. If we convert from the primal to the dual formulation, then in many cases we end up with a problem that can be framed in terms of dot product operations. And that opens the door for using kernels so that those calculations that we might want to do as linear operations in some expanded space can be done much more efficiently in terms of these kernel functions. And as we saw, that can lead to major efficiencies, especially if we have things like images or documents with a lot of substrings in them. And we know that there's some complicated nonlinear function we need to be learning. And so our alternatives are explode this into some higher dimensional space where we can learn a linear function, or try to learn something nonlinear down in the low space. And the interesting thing about these the kernel regression algorithm that we just talked about is that even though we're learning highly nonlinear things, that kind of kernel regression does have a closed form solution. We saw what it was. And we're getting the global optimum when we solve that, even though we're learning highly nonlinear functions down in this space. So it has that nice property that we always look for, that not only do we have an objective function we want to optimize, but we actually have an algorithm that can be guaranteed to find the global optimum for it. So kernel regression, very powerful idea. Okay. Regression. What about classifiers? Well, you know, regression and classification are closely related. Here's a very simple classifier that can use kernel functions. This reminds me a little of the discussion we just had about Fisher linear discriminant. But suppose we want to build a classifier where in the expanded space we have a bunch of points which are positives and a bunch of points which are negatives. And what we just want to design a classifier where we find the center of mass of these two things and then classify a test point essentially by setting some threshold on the line between them. This, of course, would be what we would get anyway if we happen to have a Gaussian classifier, assuming Gaussian naive Bayes classifier, for example. So then we can represent our learned function given some new vector x, what we'd label that positive or negative. We can represent that this way. We'll say, well, we'll take x and we'll look at the sign of the following quantity. And what we're going to do is we're going to explode x into some higher dimensional space, phi of x. Look at the difference between its point in that higher dimensional space and the mean of negative examples in that higher dimensional space. So we have to explode all those too. We'll look at the square distance from the mean of the negative examples exploded with phi versus the mean of the distance from the mean of the positives. So which one is it closer to in the exploded space? And then here's a simple re-expression of that in terms of the kernel functions. So instead of looking at the point x and how far it is from the mean in the exploded space, we can replace that. You have to prove this to yourself if you want. We can replace that by instead summing over the training examples. Dot products with all of those positive examples performed down in the base space with a kernel function k. So here's an example where, you know, the obvious way of doing this would be to explode the points, calculate what's the mean of the positive examples, find the distance from point x in the exploded space to that mean. And if you want, you can skip the step of calculating the mean. Instead, just get dot products of the new x with all of the known positive points. And that'll give you the same, this will give you the same answer as that. But now that you've expressed it as a dot product operation, we can do it just with kernel functions instead of exploding up into phi. So that's the flavor of how we like to use this kernel trick. We like to take algorithms that we can think of in simple terms up in some exploded space and then say, can we derive an equivalent thing that only requires doing dot products? And if so, we can use kernel functions. Okay, so there's the idea. It's one of my favorite advertisements for support vector machines. I don't know how many of you were around during the G20 conference. there were a lot of protests going on at the time. This guy here is Burr Settles. He's a postdoc working on the never-ending language learning project that we talked about a little before. Okay, so support vector machines. Support vector machines are just a little tweak on kernel linear regression that we talked about. So you already know most of what you need to know to pick up support vector machines. So we're going to, but now with support vector machines, we're interested in classification problems. And if I have a bunch of positive and negative points, and eventually we're going to make these in an exploded space, but for now we don't need to. And if I ask you, what's the classifier you would like? Would you like that classifier, or this one, or this one? There are different ways you could say, well, I want the one that's going to minimize the sum of squared. We're doing classification here. You have to make up an objective function. And what support vector machines do is they go with the following. They say the objective function to be optimized with a support vector machine is to maximize the margin, is to pick the decision surface that has the largest margin. And what do I mean by margin? I mean, once we have the decision surface, we look at this distance, the distance to the closest positive examples, and the distance to the closest negative examples. And the sum of those is the margin. That's kind of how much space there is. If we put that decision surface right in the middle, it's twice the distance to the closest point. And if you think about it, if I drew this other line, which would also perfectly classify the examples, but now it has a much smaller margin, right? Because I only have to go there and here. So those black lines are longer than both of the red lines. That black line has a larger margin. It's very sensible if you happen, for example, if these were Gaussian balls of data, then we would kind of expect on average going where the margin would be largest would be good, at least if they were linearly separable data points, because it kind of puts us far away from both points. It means those Gaussian distributions that have the lowest chance of giving us an example that we're going to misclassify. So at this point, I'm not going to try to justify it more than that intuition. But we may say more about this next class. But for now, let's just say, here's how we formulate it. We say, first of all, we want the decision boundary with the largest margin. And second of all, we're going to essentially convert this classification problem into a regression problem, where we label every negative example -1 and every positive example +1. And then we're going to solve it as though it was a regression style equation, but with this other objective function, maximizing the margin. So let's see how that looks. First of all, we're going to learn, just as we did in linear regression, a weight vector, W, that we multiply by x, and we'll also give ourselves a constant so that this thing doesn't have to go through the origin. But basically, we're going to learn a function, just like our linear regression function. And given any x, any point in this plane that we're looking at, if the value of that function is positive, we're going to call it a positive example. If the value of the function is negative, we're going to call this a negative example. And it's a linear function. So that is the framing. It's just a simple way of setting up classification as thresholding a continuous function that we're computing. And so now, given that, we can start doing a little bit of arithmetic to figure out what is the margin? What is the value of the margin? So think about it this way. Here's my decision surface in the middle. That's the one that separates the points on the plane for which this regression function is going to produce positive values versus negatives. You know, just like the original linear regression problem we were thinking of, if my points all lie in some plane, then the y value, you know, all my x's are just these two-dimensional points in this plane. I can think of the function, the y values, as a function of x's, as just this plane running through like this. If I have an x point over here, the value is this. If I have an x point over here, the value is this. And linear regression is nothing more than learning some plane in 3 space so that every point down here in 2 space gets a y value. That's a linear function of it. So if you think about it this way, then what we're doing here is exactly the same thing. Here's the two-dimensional space in which the x's live. Since this is a linear function, my y values, or wx plus b values, are just going to be some plane that comes out of this surface and whose distance from the screen is the y value that it's predicting. And if y is, and so for any w that I pick, I'm going to get some linear function, and I'm just separating out points where that function is giving me positive versus negative values. Okay, so now what we want to do is set up this optimization problem so that we can maximize the margin. So let's look at this typical scenario. Here's a set of points, and my margin is 2 times gamma. Here's the decision surface that's halfway between, and the distance to the closest positive example and the closest negative example is gamma. The margin is 2 gamma. Oh, here, I see. Here we're defining it as gamma. People do it both ways. It's actually more common that people would say the margin is 2 gamma, but gamma is this quantity. It's the distance between where the function equals 0 and the closest positive point. So, and let's suppose, since this is a linear function, of course, there will be some constant, a, let's call it, for which at these points, wx plus b will be a. And of course, for these, it'll be minus a, because it is a linear function. Okay. So it says over here in the box that we can express this distance, gamma, as a divided by the magnitude of our weight vector w. Is it obvious? I don't think it's obvious, but here's why. Remember, we started by saying we could think of weight vectors as vectors in the same space. They're spanned by the training examples. In fact, the weight vector for any decision surface like this one is going to be a vector that's perpendicular to the decision surface. Why is it perpendicular to the decision surface? Because informally, because if we're going to get an x dot product with that w is going to give us the y value, then the steepest, the direction of steepest increase is aligned with w. Remember, we said that all other things being equal, if things were aligned, cosine of theta equals 1, that's where we get the biggest dot product. So w is going to be perpendicular to this decision surface, and the function is going to be ascending most steeply if we move in the direction of w. So given that fact, we could look at it in the following way. We could say, let's make up, let's take some point here. Let's call it x, and for which this function equals 0, wx plus b equals 0. And let's add in a vector, I'll call it, let's add in this vector to it, of length gamma, and I'll call that vector x gamma just for the sake of argument. So now think of it this way. What's going to be, we know that because that puts us on this line, which is the line where wtx plus b equals a, we know that w of, let's call this x1 just so they both have names, x1 plus x gamma well, let's see, I want to use my same notation. So W transpose times this new vector at that point plus B, that does equal A, because that puts me to this point, which is on the line where it equals A, right? And, well, I can just rewrite that. Oops, equals A. And what does this equal? So there you have it. And what is this? This is the dot product of two vectors which are collinear, right? We agreed W is perpendicular to the decision surface, and so is this. So the cosine between those two vectors is theta 0, cosine is 1, and the dot product is just the magnitudes of these two vectors. So in other words, the magnitude of W times the magnitude of x gamma equals A. And what's the magnitude of x gamma? Well, we already said this is distance is gamma. Which is what we say. Okay. So there's this nice relationship between the magnitude of our weight vector, this margin, well, and that's it, and this margin, and the value of the function that we get at the margin. So now we can set up, next time what we'll do is we'll use this to set up an objective function. You can either peek ahead at the slides or you could think about this yourself. How would you set up the objective function that we want to optimize so that we want to maximize this margin. We want the arg max over W of this margin. That is what we're saying we want. And so we'll finish that next time. And then we'll also just, in a very quick step, point out that, of course, you can kernelize all this because we're going to be working with the dual form of the problem where everything is dot products, and you already know how to kernelize things once it's dot products. So that's for next time. Hey.